Good evening. Y'all left out the word distinct here. We're looking for the distinct prime factors. Of this expression. Now, we might as well give it a name, although it's probably not that important. Let's say this whole thing is equal to n. Okay, bunch of cubes. Okay, what we're actually trying to find right here is omega of n. And that just counts the number of prime factors, notwithstanding, like, what I'm trying to say here is that, let's say 5 to the 4th was a factor of this entire, of n. We would only list 5 one time, okay? Now, let's move along with that in mind. Now, this thing has the fortunate expression of this factored form. If you guys remember, a plus b quantity cubed has 4 terms. If you subtract off the first term and the last term, this is what you end up with. That's not hard to verify. Now, this in turn factors. So you see, we have this entire object, which is 3 different large numbers written as the product of 2 things for the choices a equals to, let's see, what a would be 6,000. And b is 153, right? Okay, so let's move along and see how this goes. Now, so in this particular case, 3ab would be equal to 3 times 6,000. And, I got the dot right in there to connote multiplication, and then times 153. Again, we don't have to be super precise about this in terms of how many of each of the factors repeat. We just need to get how many. So we know already that 2 and 3 would be prime factors, right? We don't care what power is. Okay, now to get 10, you need 5, right? So we already know just this part alone would account for 2, 3, and 5, right? In fact, that's the only ones involved here. 2 times 3 is 6. 2 times 5 is 10. You have 10 cubed, which is 2 times 5 cubed, right? So this is all that we get out of just this part right here, okay? Now what about 153? Well, this is the same as 9 times, let's see here, 3, AB, 153. That's 9 times 60 or 17. Okay. All right, now let's see. Do we have everything here? We have 3 times AB, which is this. Oh, yeah, we have to put also times. I left that out. A plus B, which is, of course, 6153. All right, y'all, so far the primes that we have, it's not too hard to obtain these. Even though these are large numbers, 2, 3, and 5 are the only prime factors of this entire piece right here. And then 9 times 17 is, of course, 153. And notice that this is just 3 squared, so you don't have to worry about adding any other primes here, right? Okay, now what about 6153? Well, it is divisible by 3. This is equal to 3 times 2051, right? Now, y'all, I'll go ahead and write the answer, but then I'll tell you how I got it. This is equal to 3, okay, times 2051 turns out to factor into 3. Well, this would be, let's just write it like this. So we have 3, and then 2051, I'll just write it like this, folks. 3 squared times 7 times 293. Now, y'all, again, I'll try to show you the work. I'm just writing the answer right now, but I want to show you how you would handle this if you didn't happen to know that 293 is a prime factor of this. Notice the 3 squared that we have right here. It comes from the 3, and then this guy right here is just 3 times 7 times 293. And you're not too impressed because, look, how do you know? Well, notice that there's this is clearly not divisible by 5. So for 7, you can do this test right here. You can do 205 minus, you can do 205 minus 2 times 1. This is the divisibility test for 7, okay? And so what does that equal to? 203? Okay, but 203, what does that equal to, folks? Is that a multiple of 7? I hope so. Isn't that equal to 7? Now 7 times 20 is 140. So 7, this is equal to 7 times, let's see, 29, right? Yeah, 7 times 29. Okay, that's 7 times 29. So this is where the 7 came from, okay? This is where the 7 came from, okay? And then the rest of it is just dividing 2051, okay? The rest of it is just dividing 6153 by 21, okay? 6153. And so you had to do the work here, okay? They don't allow you to use calculators, but 6153 over 21 is equal to 293, okay? So yeah, let me write down all the prime factors and get them all in one place. The answer would be 2, 3, 5, 7, which we just found it there at the end, sort of. 7, 17, which we found early on. And then the hardest one, of course, is 293. And I just wave my hands and says 293 is prime. But you can check that fairly easily by noting that 17 squared is 289. Okay, 17 squared is equal to 289. And so you don't have too many prime factors to check, right? See, and really the point here is that means that 293, 293 is greater than the square root of 289, right? The square root of 293, excuse me. Square root of 293 is greater than the square root of 289. And that means all you have to do is check all the divisors less than 17. Okay? So anyway, it does take some time to verify that 293 is a prime number, but it is. So anyway, that is the solution, folks. We have actually 1, 2, 3, 4, 5, 6 distinct primes. And that would make, are we up here somewhere? There's something called the omega function. Remember our number, we called it n. So what this really intimates, we didn't ask for this, but omega just counts the number of distinct primes. So omega of n is equal to 6 here. Okay. But again, this is the answer we were seeking. 6 distinct prime factors when we're not interested in their powers. Okay, I think I kept it on the same screen. So yes, this number, this unpronounceable number right here, only has these 6 divisors as prime divisors. Okay, thanks for viewing.